In this video, I want to look at sequences and series. Let's start by taking a look at sequences. I really want to emphasize that there is a difference between these two things. So sequences are just lists of numbers. So for instance, if I had the numbers 1 over 1, 1 over 2, 1 over 3, etc. And they just kept growing, the denominators kept growing. I could call this a sequence, I'll call it AN. But what I could see is I can write this AN in a more concise fashion. I could write AN as simply 1 over n, where we see that this n continues to grow. So for instance, if I were to look at A1, that would be saying the first element in the sequence, that would be the 1 over the 1. If I were to look at A2, that would be looking at the second element in the sequence, that would be the 1 over 2, A2. Or if I were to look at, say, A15, we can figure out the pattern. That would be saying the 15th element in the sequence, that would be 1 over 15. Now the sequence, we see these numbers just get smaller and smaller, 1/4, 1/5, 1/6. And so eventually what they're going to get really, really close to is 0. And so what we could say about this sequence is that it converges. So the question is, how do we tell if a sequence converges? Well, one of the easiest ways to do it is by looking at the limit. See, what happens if I allow this n to continue to grow more and more and more? So let's take the limit as n goes to infinity of 1 over n. Clearly, as the denominator grows, this fraction as a whole goes to 0. If I were to look at a different sequence, let's say we have sequence Bn, and let's say that this sequence is just n, meaning the first term in the sequence would be 1, the third term in the sequence would be equal to 3, the 15th term in the sequence would be 15. What we see this time is the numbers continue to grow and grow and grow. So if we were to take the limit as our n goes to infinity of n, well, this sequence is going to infinity, meaning it diverges. And so some are more complex than others, right? Anytime we have a limit that's more challenging to find, we might have to use other tricks. So for instance, we might have to use L'Hopital's rule, but it could be something beyond just working with the limit. So for instance, anytime we have a cosine or sine, that is something that we can't find the limit to, right? If we had, say, the sequence, we'll call it Cn, equals cosine of n. Well, as n's get bigger and bigger, this thing just continues to go up and down, up and down, up and down. So this one also fails to converge. It doesn't go to a single value. It diverges. Because there is no limit as n goes to infinity for the cosine. That fails to exist. But what if I stick that with that original 1 over n? Well, cosine, as we saw, doesn't converge, but that n going bigger and bigger does cause a convergent sequence. And so here it might be helpful to try and get rid of that cosine. I want to view it without the cosine. Well, what we know about cosine, if we look at the above examples, it goes from -1 to a +1. That is its range. And so what I could do is I could say, hey, you know what, this dn, this sequence has to be less than, say, 2 over n. It has to be greater than -2 over n. Why did I choose 2? Doesn't matter. I could have chosen 15 and -15. I just need to choose something above 1 and something less than -1. And then if I look at both of these sequences, I know that both of those converge, and because they both converge to 0, well then that tells me that my dn must converge to 0 as well. So we have several tricks to help us figure out when something converges or diverges, because we can't always just take the limit. If I have to taken the limit of my cosine n over n as n goes to infinity, I might say, well, you know what, that cosine n just, I don't know what it does. It continues to bounce around, so I don't know what that does. We can put that dn between two other sequences that we do know what they do, and then that allows us to state that it does in fact converge. Let's talk about series now. Well, with these sequences, we've just been looking at individual terms. We've never said, let's put it all together. So for instance, if we look at our first example, we had that 1 over n. We saw we had the term 1 over 1, then we had the term 1 over 2, 1 over 3. Just had all these individual terms here. But what if I want to put them together? What if I want to add them together? Well, that's when we get to our series. And one way we can add very efficiently a lot of terms is by using the summation symbol. Summation. And I'm going to let my n go from, in this case, 1 to infinity. And let's use that original sequence that we started with, the 1 over n. So I've taken the sequence 1 over n and I've placed it into a summation. This is now a series. So series, we are taking terms, or we can think of them as elements of a sequence. We're adding them all together. That's the key. We're adding all those together. Now the question is, does this have a value? Sometimes when we add up these series, we will get a single value. Sometimes, however, this series does what's called diverge, means it doesn't have just one value, or it continues to grow more and more and more. Now, if I call this series, call it Fn, well, I can find a partial sum. I can find what several of the terms would be equal to. So for instance, let's say I wanted to find S of 2. Well, that would be 1 over 1 plus 1 over 2. I'm adding together what I get when I plug my 1 in, because my index here was n equals 1, so I start there. I'm going all the way up to 2. 1 plus 1/2 would be 1 1/2 or 3/2. I could do the same thing for S3. I'd have 1 plus 1/2 plus 1/3. I add those together. That'd be 3, 6, 2, 6, 5, 6, or 11, 6. 1 and 5, 6, 11, 6. When we said the sequence 1 over n converge, but that does not mean that the series does. It could be that when I add these things together, it actually diverges, means that we don't actually get a sum. We can't add it together. And this is one of those examples. 1 over n is a great example of a sequence that will converge, but when we take its sum, when we take the series, summation n equals 1 to infinity of 1 over n, that actually diverges. This series right here is called a harmonic series. Harmonic series is always just 1 over n as n goes to infinity, and that will always diverge. And so I've listed out several of the first terms, but let me just continue to list out more terms. So if I look at the harmonic series, we start with that 1. We then get a plus 1/2. We get a plus 1/3, plus 1/4, plus 1/5. And it's just going to keep going more and more and more. But let me list out a few more still, because then I can really combine them in kind of an interesting way, unique to the harmonic series. And I just use some ellipses real quick. Continues all the way up to 1 to the 16th, and then, of course, it would continue from there. Put my dot, dot, dot in there. Let me start adding these together, though. 1 is obviously 1, but let's look what happens if I take the, let me add the 1/3 and the 1/4. If I add 1/3 and 1/4, that is something greater than 1/2. That's approximation. I don't care exactly what its value is, but I know it's greater than 1/2. If I add the next 4 terms, that is also greater than 1/2. If I add those next 8 terms, the 1/9 through the 1/16, that is also greater than 1/2. So what I see is I started with 1, I add to it 1/2, the next 2 terms adds to 1/2, the next 4 terms adds to 1/2, the next 8 terms adds to 1/2. I can continue to do this over and over again. So what I'm doing is I'm adding a bunch of 1/2s. If I continue to add 1/2s, which I have to do, it's just doubling the number of terms each time. If I continue to add those 1/2s, well then we're not getting a single valued sum. And so what that's telling me is this is growing more and more. It does, in fact, diverge. This time let's look at something that converges. So let me take the sum from n equals 1 to infinity of 1/2 to the n minus 1 power. So if I were to start to write out what those terms would be in this series, I would have 1/2 to the 0 power, which I think the 0 is 1, and we'd have 1/2 to the first, which is 1/2, 1/2 to the second, which is 4, 1/2 to the third, which is 1/8, and it continue in the same pattern. These numbers are getting smaller just like they did before, but at a much faster rate. And notice I can't, to find where they're equal to that 1/2, take a lot longer, take more terms. And so for this reason, this one doesn't end up at that problem of having 1/2 plus 1/2 plus 1/2. There's no pattern we can find to add up those 1/2s. This series here is going to converge. Now, I'm going to skip a few steps. There is an explanation for geometric series in another video, but this is a geometric series. And so we know that anytime we have the geometric series, n is equal to 1 to infinity of series has some coefficient, but then if we have an r value raised to the n minus 1, as long as that r value is less than 1, which ours is, it's 1/2, well, that summation will always be equal to a over 1 minus r. If I look at my geometric series, I didn't have a coefficient, meaning my coefficient was a 1, and my r values was a 1/2, and so we have 1 minus 1/2 on the bottom, or 1 over 1/2, which is equal to 2. So because this series converges, then we can find its summation. Because the series converged means we're going to get to a single value, and that single value in this case is the 2. So what we saw is just because a sequence converges does not mean that the series will. This sequence, 1 over n converged, the series diverge. So the question becomes, when do series converge and when do they diverge? And that takes sometimes a little bit of work. It's not always as easy as these two problems. And so we have a list of things that can help us with that. We have the nth term, the divergence test. We have the integral test. We have the limit comparison test. We have the direct comparison test, ratio, root test, alternating series test. So we have all these other tests that you're going to study, you're going to see videos for. But that's going to be our goal, to determine when do these things converge, when can we get that series value, that summation value, versus when do they diverge, meaning those values are just going to continue to grow and grow and grow. So anytime we have these sequences, we have just single terms, not being added, subtracted in any way. We just have a list of values. Those can converge or they can diverge, meaning they head to a single place. When we want to put terms together through addition, that's when we've transitioned over to a series. We have our summation. Those again can either converge or they can diverge. Converging means we'll get a single value, and sometimes it's hard to figure out what that value will be. Sometimes it's much easier to tell simply, does something converge or does it diverge, rather than to actually figure out what it converges to.